Hello, my name is Tom Van Goethem, and in this presentation I'll be talking about leaking browsers. So I'm a security researcher from the TCNet group at the University of Leuven, and in this presentation I'll cover some of the research that I've done over the years. So both very recent work as well as research from a couple of years ago. So let's take a look at the modern day browser. So browsers, well, usually when you visit a website, the first thing that the browser needs to do is fetch the content from the web server. This will be over an HTTP2 or HTTP 1.1 connection, and typically over TLS over TCP. Once the resources have been fetched, the browser will have to process and render them. In order to improve performance, websites can also make use of caching and local storage. And next to that, the browser supports a gazillion of features. And well, some of these features cause some side channel information to leak, and this is what we in this presentation will be abusing. So let's first take a look at the threat model. So here we have our modern day browser, which we use to visit our secure bank. Of course, we have to authenticate with the bank. So for this, we will use cookies, which are stored in the cookie store or the cookie jar of the browser. Of course, the secure bank is not the only website that we will visit, so we might also look at some interesting pictures of kittens. Unfortunately, this site may not always have our best intentions in mind. Or it could also be that it's serving content from or including some content from a malicious website, so it could be that it's compromised in some way. And well, this compromised or malicious website can then send back some malicious JavaScript files, which will be executed in the browser. And in this case, they will try to infer some information from the secure bank. So an attacker may try to leak certain security information, such as the cross-site request forgery token. And well, if that happens, that may lead to a full account compromise. So for instance, the attacker could change the email address and passwords from the victim. Another thing is that the attacker may try to determine the identity of the user by using a spear phishing attack, or try to use it for profiling the user. A third type of attack could be that the attacker wants to perform certain search queries under the credentials of the user, which may be abused to, or which could be abused to leak secrets that only the victim has access to. So for instance, by searching the mailbox of the victim for certain terms, it might be possible to leak information from this mailbox. And alternatively, the attacker might try to extract some privacy sensitive content, for instance, to try to determine which websites the user is logged into. And well, in order to obtain this information, the attacker will make use of techniques called cross-site leaks or XSLeaks, and these try to violate the same origin policy. And the same origin policy prevents site A from accessing information or any information about the contents of resources located at site B. So these cross-site leaks, they will try to abuse side channel information in order to leak this metadata. So for instance, this could be the timing of the response, the firing of events, so either the order or the time at which the events were fired, or getting the size of the response, or any other type of meta information. And why it's useful is because this metadata is often dependent on the state of the user. So for instance, if a search query has results, then the server will respond with a large response. And if there's no results, well, the server will respond with a small response. And if the attacker is able to determine whether the response is large or small, they can know whether the search query returned results or not. So there's different types of categories for cross-site leaks. So for instance, we have the status of the response. So this could be a redirect. For instance, if the user is not logged in, it will be a redirect to the login page or a 404, etc. So there's different types of ways to determine this. Another thing is the cache status. So if a resource has been cached, it will be loaded much faster because there's no network connection needed. And the attacker can use some timing information to determine this. And then third thing would be operations that are performed when the resource has been rendered. So for instance, it might be possible to determine the number of frames that are in a web page. Or if this web page sends a post message to the embedding document, it might also be possible to capture this. So in this presentation, I will focus on two specific types of cross-site leaks, and one is determining the response size. So for this, we will use two techniques. So on the one hand, the browser-based timing side channels. On the other hand, heist, which stands for HTTP encrypted information, can be stolen through TCP windows. And the other thing that I'll be looking into is determining the processing time of the server by using a very new technique called timeless timing attacks. So let's look at the scenario from before where we visit this malicious site, and this site will trigger a GET request to transactions to Tom VG. It will send it to the side of the bank, and unfortunately there were no transactions to Tom, so it will return no results. And then this malicious site will either use some timing information or will try to measure the size of the response in order to extract some information from this. So it will be able to determine that there were no transactions to Tom. Then it will send another request, or it will trigger this request to be sent to the bank. And it will try to get the transaction sent to Hexor. And well, then we can see that the current user, so in this case the victim, made 17 transactions to the Hexor. And well, this response might take a bit longer to generate because, well, the server needs to include all the information about all the different transactions. So by using timing informations, it might be possible to infer that this current user made transactions to the Hexor. And also the response will probably be larger, which can be determined by the techniques that I'll be talking about next. So the most simple way to perform a timing attack is by, well, starting your timer, then making a GET request, or like a fetch, and then when the promise of this fetch request resolves, so that's when this function in the then executes, and then we can stop the timer, and we just take the difference between these points in time. So this will measure the time it took to download the resource. Unfortunately for the attacker, the accuracy of such an attack will largely depend on the internet connection of the victim, which, well, of course, is not under control of the attacker. And if there's a lot of variations in the delays of the packets, so if there's some jitter, then the attack may no longer be effective or efficient. So what we as an attacker need would be an attack that is not affected by any of these bad network conditions. So here's an example of this. So here we create a video element and add two event listeners, one for the suspend event and the other for the error event. And this suspend event will fire when the resource has been downloaded. So and the error event will fire after the browser tries to parse this resource, which is not an actual video, as a video, and well, it will fail to do so, and it will throw this error event. So this means that the timing will start after the resource has been downloaded, which means that it's, of course, not affected by any network conditions. And an interesting aspect is that the time it takes to parse a certain resource as a video will depend on the size of this video or of this resource. So this is something that we found a couple of years ago and then reported to the browsers. And now it's been largely mitigated. So what happens is that the browser will not actually parse the video when it determines that it's not actually a valid video. So it will not try to parse the entire file. And well, in Chrome, this is because of the cross-origin read blocking. Because if we try to because the HTML, XML, and JSON content is not allowed to be in the same renderer. So this mechanism will prevent the video from being rendered. And for Firefox, they perform some MIME type checking, so they will not actually process the video. And then another technique is by using the cache API. So here we first fetch the response, and then we start a timer just before adding this response to the cache, so the programmable cache. And we stop the timer after we've put it into the cache and we've deleted it. And well, the time it takes to put it into the cache and delete it from the cache is related to the size. So using this, we can get some estimate of the size. So in our experiments, we found that it was possible to get an estimate of around 5 kilobytes in the file size. And in Chrome, this again has been mitigated by the cross-origin read blocking mechanism. But unfortunately in Firefox, it's still possible to exploit this. So these were two examples of browser-based time attacks. The interesting aspect of these time attacks is that we measure the time it takes to perform an operation after a resource has been downloaded. So this makes that they're not affected by network conditions. So there have been already some effective countermeasures, and that is to discard all operations on cross-origin resources as soon as possible. So If the browser knows that this shouldn't be processed, then it can already stop processing it, and the timing of the processing will not depend on the size of the response. And that brings me to the second type of attack, so heist, where we will try to determine the exact size of a response by using TCP windows. But before I go into the details, let's first look at what happens when we do a simple fetch request. So we have our GET request to the server, which will be encrypted using TLS. And then, because it's a TCP connection, it will be, well, put into a TCP packet. And in this case, the request might be something like 481 bytes, so it's fairly small. And then the server will generate a response and send it back to the server, to the client. And again, put it into a TLS connection, a TLS record, and also a TCP packet. But as you can see, the content of this response is 9,840 bytes. However, we can only put 1,448 bytes into a single TCP packet. So this means that we will need one additional TCP packet for the rest, and one more, and well, actually several more, until every the whole content of the response can be put into these TCP packets. So let's look then how these TCP packets are sent to the client. So of course, the first TCP packet will be sent. Right after, it will send the second, and so on, until we have sent 10 TCP packets, which equals one TCP window. And afterwards, the server will have to stop or have to wait with sending the rest of the response until the client sends an acknowledgement to the server. Once this acknowledgement has been received, the server can start sending the rest of the response. So this means that if the response size is larger than what can fit into 10 TCP packets, so that's around 14 or 15 kilobytes, then the server will need to wait for the acknowledgement. So this means that there will be one additional round trip to receive the response. So as I've said, so if it's less than 14,480 bytes, everything will fit in a single TCP window. If it's more, then multiple TCP windows are required, because the server needs to wait for the TCP ACK from the client, which will require an additional round trip. So if we have some kind of mechanism to detect whether one or multiple round trips were required, we can leak information about the size of the response. And that's exactly what we will do here. And so we fetch this first URL, and when this promise resolves, we know that the first byte of the response has been received, and then later on we use the performance API to get the entry associated with this fetch, and look at the property response end, which will indicate when the last byte of the response has been received. So if there's difference in time between the last byte and the first byte is less than a certain value, so for instance 5 milliseconds, everything will fit. Well, it means that only a single TCP window was required, so everything fit into the single TCP window, and otherwise multiple TCP windows were required. So one additional round trip might be something like 50 or 100 milliseconds. So it took some time before these were could be sent. So that's well, that was how we could determine the size of the response. And now another important aspect is gzip compression, which is enabled on most of the resources or most of the responses sent on the web. So let's look at a template that looks like this. So welcome, then the username, which is from, for instance, the get parameter, and later in the document there's some secret occurring. So when it says welcome Tom, then nothing special happens. But when it's welcome secret equals, then this 7 characters of this secret equals that occur later in the document can be replaced with a back reference to the first occurrence of this string. And this means, well, then we can start guessing character by character. So first we have secret A, secret equals A, which is, well, A is not a valid guess. So the response side will be 1 byte less than if it would be a correct guess. So on the right hand side we have secret equals capital N, and as you can see the back reference grew to 8 bytes, which means that we only need 1 byte less to compress, well, after compression. So it will be 1 byte less if it's a correct guess of the response. And now we can put the two things together. So if we guess correctly, we have 1 byte less. And then what we can do is make sure that the resource, if it's a correct guess, fits into just one TCP window. And we can do that by, for instance, reflecting URL parameters. So increasing the response size by adding things in the URL parameters that are reflected in the response. And then when we, well, then we start guessing the secrets 1 character at a time. So if it's if it's a correct guess, we will only need a single TCP window, because if it's an incorrect guess, we will need 1 byte more to send the response, and 2 TCP windows are required. So that means that we need another round trip, and using this technique with the performance API and the fetch API, we can determine whether it was 1 or multiple TCP windows that were sent. And this allows us to leak secrets such as CSRF tokens byte by byte. So that were the 2 techniques that we can use to either get an estimate of the response size or get the exact size, and after, well, the exact size after compression, which allows us to leak secrets byte by byte. And now we will look at how we can try to determine the processing time of the server. And for this we will look at a technique, a very recent technique called timeless timing attacks. So this is the example as before, which is a very basic way of trying to determine well, the processing time of the server. But unfortunately it's heavily affected by network jitter. So we were wondering, can we do any better? And it turns out doing better is relatively easy, or, well, without the technical details, it's relatively easy. So concept-wise, it's easy. So instead of just getting or sending 1 request at a time, we will send actually 2 requests, and then we will try to determine which one sent a response back first. And well, the one that sent a response back first, it means that it was generated faster. So there's some, well, requirements for this to work. So first, a very important one is that 2 requests need to arrive at exactly the same time. So this means that they should ideally be in the same TCP packet arriving at the server. And both requests also need to be processed in parallel. so concurrently. And if these two conditions are checked, then we can determine which request took longer to process just by looking at the order in which the responses were returned. And so for this attack, it will, well, in the browser, it will only be possible to exploit it over HTTP2. So in HTTP2, there's a major improvement. Or one of the major improvements is the support for concurrency at the network level. This allows us to execute multiple requests in parallel over a single TCP connection. And then we also have to ensure that both requests are in the same TCP packet. And for this, we can again use the trick of using TCP congestion windows, because this algorithm also applies to the client. So what we can do is we can first send a very large request to the server. So a request that's larger than a single TCP window. And then the client needs to wait for an acknowledgement from the server before sending the rest of the request. And while waiting for this acknowledgement, all the requests that follow will be added to the same TCP packet. So let's look how this works. So first we have our large post request, which contains which will fill the first TCP windows with 10 TCP packets. And then on the network stack, it will already start queuing the rest of the response. And then when the browser wants to make more, when the browser makes more GET URLs or makes more requests, then this request will be added to the TCP packets of this large request. And then at the same time, a second GET request is sent. This will be added to the same TCP packet. So only when the acknowledgement from the server arrives, the packets that are still in the queue will be sent to the server. And as you can see, both GET requests that we're interested in will be sent in the same TCP packet. So this means that they will arrive at exactly the same time at the server. So, in code it looks fairly easy. So first we make the post request and then the two fetch requests, and we just determine which one arrives first. So why would we need this timeless time index? So the interesting or exciting thing about it is that it can distinguish timing differences up to 100 times smaller. So this means that these time index are approximately 100 times better than the typical timing attacks that we know today. So in certain cases, we can distinguish timing differences as small as 150 nanoseconds. So it's possible to, using these techniques, it's possible to exploit timing attacks that were previously considered not possible to exploit. And another interesting thing about it is that it's a very generic technique, so it can be applied to every server that runs HTTP2. And there is some side note, and that is that although it may look like the server is using HTTP2, for instance with CDNs, the connection to from the client to the CDN might be HTTP2, but from the CDN to the actual server might still be over HTTP1. So that may pose some limitations, but still it's very likely that the attacks will still be much better than the classical timing attacks. So I've been talking a lot about different types of attacks, but I also briefly wanted to cover the different types of defenses. So fairly recently, there has been an explosion of different types of security features that are being added to modern browsers that aim to fix the web. So some examples are the cross-origin read blocking, cross-origin resource blocking, the cross-origin resource policy, the cross-origin embedder policy, the cross-origin opener policy, and then same-site cookies and the segfetch headers. So I want to go into much details of these, all the individual defenses, but I strongly advise people to look them up online. There's already been some very nice resources that you can find to learn more about them. So these security features aim to limit the bad functionality that has been pestering the web. So for instance, cookies should not be included in all cross-site requests. This is a source of many different type of vulnerabilities. And another thing is that it shouldn't be possible to just play around with cross-site responses, or just play around with or interfere with cross-origin windows without any limitations. So these security features aim to limit this. Some of these features will be enabled by default or are already enabled by default, which makes, I believe that this makes them most effective because it will protect all the users on all the websites. But of course, the browser vendors need to perform some balancing act between finding a balance between what will break existing functionality and guaranteeing the security of the users. And this brings me to the conclusion of this presentation. So we know that browsers will leak some metadata information about cross-origin resources, and this metadata can be used to extract sensitive content from the users. So in this presentation, I've been talking about different types of attacks. So on the one hand side, trying to leak the size of responses, either as an estimate with a browser-based timing attacks, or get the exact response size by the techniques of that are based on the TCP windows, so the heist attacks. And there we could actually extract the content of the responses, or some content of the responses, because they were using gzip compression. And then another very recent technique is want to leak the processing time of the server. And in our research, we've shown that it's 100 times more accurate than the classic timing attacks. And an interesting aspect about all these different types of attacks is that they're all independent of the network conditions of the user. So these attacks are fairly bad and not entirely mitigated yet. Hopefully in the future, with the new security features, we will be able to remove the bad legacy features from the browsers and improve security overall. But I should note that in some cases, so for instance, these timeless time attacks, some intervention or some efforts from the websites is still required. And this will always be the case. So this concludes the presentation. If you have any questions, I hope that I will be able to answer them. And if you think of something or just want to further discuss this presentation, don't hesitate to reach out to me. So you can contact me on Twitter or via email. Okay, thank you.
Tom, thank you for the great talk. We have some questions from the audience. Again, I don't mean to start a holy war, but someone in the audience is trying me to. Which browser do you use for your laptop? Can you recommend this? Which browser is the best, quote unquote, from a security perspective? Now it's your burden.
So I don't think there's a best browser out there. I think part of the web thrives because there's different browsers out there, which makes it, browsers need to cooperate to make the web better.
Mm-hmm.
As in terms of security, it's tricky to say. So on the one hand, you might want to have a browser that's, you definitely want to have a browser that's being actively developed and where people or the developers implement stronger security guarantees. But on the other hand, that also often implies that there are more features being added to that browser. And typically more features means more vulnerabilities. So it's a bit of a, you need to weigh it. So yeah, I'm kind of trying to not give like a specific browser. Because I don't think there's, I don't actually think that there is one where you can say, okay, this browser is 100% better than another one. I think it mainly depends on like the goals of the browser on one hand. So there's several browsers now that have been adding privacy features. So if you want to have like a more privacy preserving way of browsing the web, then browsers such as Brave or Firefox or even the Tor browser might be good for you.
You did it.
Yeah.
You did it without harming anyone. I wouldn't. So the next question is, again, it's a provocative one. If you would give just one single advice, how to protect from XSS attacks?
Do you mean XSS or XSLeaks?
XSLeaks, I guess.
Okay. So I think the thing that is defending the most will be same-site cookies. That I think will be the most comprehensive defense. And hopefully that will be enabled, or it might have already been enabled by the default in Chrome. So I hope that the other browsers will follow there as well.
Good.
So the reason why it is because if there's no cookies attached to the request, then there's nothing private that can be leaked.
Mm-hmm.
The only problem or possible problem is that that covers the currently known cross-site leak attacks.
Mm-hmm.
But it might be that in the future there might be different ones where, for instance, you pre-render something or you open something as a different window, and then it could be that there might still be things leaking. So it doesn't cover everything.
We will deal with that then. Okay, then next one. Is it possible to randomize the authentication/identification ceremonies timing to mitigate heist?
Could you say that again?
Is it possible to mitigate heist by randomizing authentication and identification, handshakes, and procedures?
So heist in itself does not have that much to do with authentication. But I think that, well, the idea of randomization is a good one. So there have been some defenses proposed where you constantly, randomize the CSRF token, so the cross-site request forgery token. And if that's randomized, then it's very tricky to, well, then you'd never get the same result. And you, with heist, you need multiple tries over and over. So that might be a good way to tackle it. Unfortunately, implementing this is not so trivial. For instance, imagine that you are browsing one web page and then you open one in another tab, and then you switch back and then submit a form there. Then that wouldn't work because the CSRF token would be randomized already.
Yeah, great, thanks. And I think the final question would be, I'm not sure whether you covered that. How long did it take you to do all this research?
The research covered in the talk was research that was done over several years. And well, not everything is, well, I wouldn't say that everything is done by myself. So I also was collaborating with people. There's also many great people working on cross-site leaks for, I think, 2 years or more already. So it kind of all, like, it builds up the number of leaks in the browser. And I also think that I wouldn't be able to find the things that I have found recently if it wasn't for the experience that I built up doing the research before. So it's tricky to say, like looking for this, it will take this much amount of time. It kind of depends on your previous experiences and the things that you discovered before. And then you kind of get an idea of where to look to.
That's, I think that several years is a decent answer, just because it gives an impression of how much work, of how many people you have to put in to get the results. Tom, thank you very much. Unfortunately, that's the time we have for the Q&A, and I thank you for being part of NoNameCon, and you are most welcome to stay online and follow the rest of the day and tomorrow.
Yeah.
And we have tweeted out your Twitter account as NoNameCon. If anyone in the audience has more questions, please refer to that and contact Tom directly.
Yeah, I'm always happy to answer questions, and well, thanks a lot for having me.
Thank you.